Okay, let us start our morning lecture. I remind you that we consider the properties of the Laplace transform, and the last property was on the previous lecture. It was seventh property, and it is called the delay theorem. And so the next property, 8, shift theorem. Press shift theorem. It says that Laplace transform such a combination is equal to f large depending on p minus p0, that is multiplication by such an exponent effectively shifts the argument of the Laplace transform. So the name is the proof. By definition, write the Laplace transform on the left hand side. And this, by definition of the Laplace transform f large, is given by this expression, because p is replaced here by p minus p0. The proof is finished. For example, that sine of omega t is Laplace transformed into such an expression. So we consider this sine multiplied by an exponential function is transformed into Conjugate ratio. Is an inevitable application of this. So the next property, convolution theory. We take it as our proof. It says that the Laplace transform of convolution of two original functions just a product of the Laplace transform of these functions. I remind you that on the right hand side of this expression, the convolution of two functions is written, which we denoted with star. And we see that according to this property, is the Laplace transform of the convolution of two function goes into is equal to the simple product of two Laplace transforms of the function f and g. Without proof. Proof is simple, but of course, we already encountered with such a property for Fourier transform. This is an element of this property of the Laplace transform. And similar property holds for invariant transform as well. That we will study in the next year. the next property. Multiplication theorem. Let f g of t be the original functions the grow indices S1, S2, respectively. Then the product is the original function. It satisfies the three properties which were imposed on the original functions, and the Fourier transform of this product, the Laplace transform of this product, is given by the following convolution. Laplace transforms the function is small and too small. There arguments of these two functions and the contour, the integration contour, which runs parallel to the imaginary axis from bottom to top along the line real part of the complex variable q is equal to a, and here is one the rows in this one and rows F. So in a certain sense, this theorem is inverse to this one, and we also take it as an example. Now, another property. An infinitely distant point equal to infinity is a regular point. Larger. And in some its punctured neighborhood, there exists a Lorentz series to this function.
What's mean the regular point?
Regular point, analytic point, where the function is analytic. The function is analytic, the neighborhood to this point. Point of analysis. And Then the original function f small of t is given by the following expression. Elementary.
One question. The Laplace transform is linear
Of course,
because the integral is linear.
yes, it was the first property of the transform. The statement of the theorem follows from linearity of the Laplace transform. And from the previous lecture, says that transform such an expression depends on the sum sign.
Yeah.
Is equal to 1 over e to nth power. And we also must apply term-wise integration of the series. Another proof is based on the inverse Mellon formula. One has to apply the inverse Mellon's formula to this series. And by simple integration, one will have finished. In fact, there was two ways to prove the statement. Some remarks. In fact, this property says that the Laplace transform maps the Taylor series into the Laurent series without principal part, or without regular part. And Notice also that the Laplace transform over T or over T to K's power K greater or equal to is not defined. So Laplace transform of the Lorentz series is principal part is not defined. As for the properties of the Laplace transform, that's it. And the next section. Oh, solution of differential equations by means of the Laplace transform.
What is the
Ordinary differential equations. Let us given an ordinary differential equation. It's constant coefficients. General form looks as follows. Generally is homogeneous, so this f is not equal to 0. And without also generality, we can assume that is 0 in that range. And in order to solve this equation, in order for this equation to possess a unique solution, we must impose in it or supply this equation with initial conditions. We also assume that function x of t, f of t, and the derivatives of x of t, which enter into this equation, are the original functions. They meet the conditions 1, 2, 3, which were given at the beginning of the previous lecture. Introduce the notation. Laplace transforms of the function x of t. You denote it as x large of p, and the Laplace transform of small of t, denoted as large of p. Then the main idea to how to solve this equation by using the Laplace transform is to Laplace transform the both sides of the equation. To find, then we will obtain an algebraic equation which can be easily solved. And after that, we express from this algebraic equation x large in terms of coefficients a, initial conditions, and f large. And after that, we perform the inverse Laplace transform and find x small. Okay, let us realize this procedure using the properties of the Laplace transform, namely linearity and the Laplace transform of the derivative of the original function. We have it's rather huge, but it's simple. All the formulas Laplace transform of the derivative, of the nth derivative of the values of the function were given. So we just substitute them here. The expressions of the square brackets are just into the Laplace transforms this derivative. derivatives of the function x. Now we see that the function x large of p enters linear into this equation, and so we will have a linear equation for the function x of t. It can be solved. Then we arrive at the full formula. Yeah. Like the terms at x0, x1, and so on, and at x large of p. It is the equation of the form. So, okay. Solution, obviously. Then small of t, that is the original function, is found by applying the inverse Laplace transform. The inverse. Then its formula. Or by using the properties of the Laplace transform when the right hand side of this expression is of some particular form that we can find the original function without applying the inverse measurement formula. Thus, we see that the Laplace transform allows us to reduce the solution of the ordinary differential equation to the solution of algebraic equation, which is much simpler task. It's a much simpler task. And then we solve this algebraic equation. We can find the original function by the inverse Laplace transform, or for example, we can find asymptotics of this function without even without explicit expression for the inverse Laplace transform. And how to do this, we will discuss next year. And discuss the asymptotics of the Laplace transform. Now we consider an example. It's formulated as a problem. Maybe find equation that means the derivative with respect to t. The full conditions also applied solution. Then by applying the method, find the function a large of p. The explicit expression being here, in fact, it's a coefficient of x large of p, and is just obtained by replacing the derivatives with respect to t by t in the respective form. And you see that in this case, this expression can be written as follows. And as follows from the general formula for B large. In our case, in the case of this example, this B large is equal to 0 because x0, x1, and so on are all equal to 0. And as for f large of p, it is a Laplace transform of unity, and we know that it is equal to 1 over p. Then we just substitute this expression into the general formula. And in accordance with the general procedure, we must apply the inverse Manin's formula, amplifying the original function x of t. But in this simple case, we can find the original function by using the properties of the Laplace transform, which were formulated and partially proved in the previous section. That we decompose this expression into elementary functions. One can check that. Then we take these fractions together, then we obtain this. So, know that first transform for unity. 1 over k minus p0 is the first transform with exponent, such a form. Theorem. And also such a formula. These formulas were proved on the previous lecture. Pardon?
Why you the 2 over p?
Because it was a general formula, and
okay.
it is divided the left and right hand side of the certain bracket. And then case is equal to minus 1. And by linearity, applying these formulas, somehow stems from the fact that we must divide this formula by the left and right hand side of this formula by. Oh, this is the answer. Example. Remarks in order. Such procedure is applicable to systems of linear ordinary differential equations with constant coefficients as well. It was a last point concerning the Laplace transform this semester, and the next section is taught harmonic functions of 2 variables. Finish. Function u of x and y is called harmonic. The domain D. Provided satisfies the Laplace transform with the Laplace equations.
Time of break.
Okay, that's break. Okay, let us continue our lecture. And move on to the definition. In terms of the linearity of the Laplace operator, A linear combination of two harmonic functions is harmonic functions, is a harmonic function. Point. The same definition of harmonic function of a harmonic function is valid for space dimension larger than 2. With the properties that we will prove below, the most of properties that we will prove below are only valid for the spaces with 2 dimensions. This case of two-dimensional space is an exceptional one. And, so we'll consider the properties of harmonic functions. Of two independent variables functions. That is easy to look at. First property. Function f of z represented in terms of its real and imaginary parts. This function is single valued. And analytic indeed. It's on domain D. Then these functions u and v are harmonic functions. Domain D. Single and is based on This is the given conditions false. Differentiate by differentiation of these equations. Find will find. Example with respect to x. Differentiate both sides of this equation with respect to x. We arrive at the following two equations, and then we see that remaining this expression on the left-hand side. That's a function, this harmonic function in the domain of analysis of the function. And another would say for function b. The proof is finished. Definition. Two harmonic functions be related by the Cauchy-Riemann conditions. Now forward conjugate. The second property. For any harmonic, for any function analytic harmonic function, for any function harmonic, which is harmonic, simply connected domain D. Function u x and y, which is harmonic, simply connected domain D. There exists conjugate. It's conjugate function. U x and y. And all these conjugate functions given by the pool. This holds. Where C is an arbitrary real constant. Such X number when it belongs to D, the fixed point. And Z can be represented in terms of complex numbers false, or it is just a pair X, Y, or there is a pair of X and Y. And so as it follows from harmonicity, that's in fact from the Laplace equation. Right, this Laplace equation form. This is nothing but the condition, as the theorem for mathematical analysis says, that of the condition of independence of this integral on the path of integration. Integration doesn't depend.
And so the line of integration is line between 0, null, and 0, or is another function maybe, or
The path of integration, the contact integration,
yes,
is an arbitrary curve that connects Z0 and Z in the domain of in the domain D, which is assumed to be simply connected.
it can be
Any path, for example, straight line, if it lies in the domain D. Doesn't depend on the integration conjugate. Of course, D is assumed to be simply connected. Therefore, hence, this formula for V is correctly defined. And V of x and y is a function that only and doesn't depend on integration contour. Let us prove that this function V is a conjugate function to the function. Because we must prove that the function u and v are related by the Cauchy functions. Let us find the derivative. Derivatives of the function, and h tends to 0 along the real axis. Then write the derivative of the function v as the formal limit. And substituting the definition of these functions in terms of the integral. We have the formal expression. Then we use the properties of the integral, and we can join these two integrals and obtain large distribution.
By minus partial derivatives by y
With respect to y. Yeah. Okay. Then we use the fact that h tends to 0 along the real axis. Y is equal to 0. That is the integration contour. Okay. It's parallel to the real axis. So y doesn't change. And and we have just the definition of the derivative of the integral. It's conversion. just a zero. So this is a definition of integral, which gives us the integrand. Taking the point that is an ordered pair of x and y. And analogously, or in the same way, we can prove that the other derivative, partial derivative with respect to y, is equal to partial derivative of u with respect to x. And thus we have shown that the function u and v are related by the Cauchy-Riemann conditions. The fact that this function conjugate to each other, and to prove that formula gives us the general solution for all conjugate functions.
So for this function, we proved what the Cauchy-Riemann conditions are true. So this formula is give us a harmonic function.
We know that the function u is a harmonic function. It is given in the statement of the theorem.
Okay.
And the theorem says that its conjugate can be constructed by the above formula. And then we just check that it is the case. And now we have to prove that this is a general solution for all, that is a general formula for all conjugate functions. Now, the fact that formula gives all conjugate functions to u of x and y follows from the fact that v for x and y is determined from the Cauchy-Riemann conditions up to an addition of an arbitrary real constant. Indeed, let's consider Cauchy-Riemann conditions. Where the function u is fixed, and let v1 and v2 be the functions conjugate to the function v. Conjugate to the function u. then, as follows from these conditions, from the function v1 and v2, write it the following way. Then we just subtract our the equation for v1 from the equation for v2, and we will have such a pair of equations. This equation can be simply integrated. Solve it. v1 minus v2 is equal to some real constant. So, if we know some particular solution of this pair of equation for Schrödinger conditions, then the general solution is obtained just by adding an arbitrary real constant to this particular solution. Thus, the above formula gives us the general solution for all the conjugate functions for the function u. The proof is finished. Early. 7.1. Any harmonic function in D doing D any harmonic function in the domain D is imaginary or real part of some analytic function.
This truly only for function with two dimensions.
Yes, of course, because the theorem says about analytic functions. We define these analytic functions, the function of complex variable, and the complex variable is characterized by two real variables, that is quantities and complex. The proof is obvious. It is obvious consequence of the previous theorem, because if one have harmonic function u, then one can always construct its conjugate function v, and then the function v plus I multiplied by v is an analytic function in the domain D, because u and y satisfy the Cauchy-Riemann. And okay, the next property. Next property. Property. Any harmonic function x and y in the domain D. Function x points towards in some neighborhood of the point f z0. Following expansion this function, this is a function u of x and y, can be represented in the form of convergent Taylor series with respect to two variables x and y in the vicinity of the point x0 and y0. Before we proceed to the proof, I'll give some remarks. The variables y, series 1 can be complex numbers. And in fact, it follows from the following observation. If we prove this formula for real values, for real variables x and y, then as it follows, this series is convergent in some domain, in some disk, in fact. And then as follows from the Abel theorem, this series is convergent for complex x and y as well, when this x and y are sufficiently close to x0 and y0. And the second remark says that we see that in fact the condition that the function u satisfies the Laplace equation implies that is that this function is an analytical function. In particular, it belongs to C infinity. Yeah. In order for this equation to be defined, you must belong to the class C2. Okay? It must possess second derivative. But it turns out, and we will prove that if this function satisfies this equation, then it is in fact an analytical function because it is expandable in convergent Taylor series, and in particular, all the higher derivatives of this function are also defined. And the proof. Follows. With a corollary. It's 0.1. There's this function, the analytical function. Of Z such that the real part of the function f is equal to u. And so the function f of z can be written function is from the statement of the theorem.
Can you down the yes?
And this function that is analytic in the vicinity of the point z0. Some open disk. We have this function. Right. That in terms of its convergent Taylor series. Simply due to the fact that, in virtue of the fact that this function is a logical function. Yeah. Cn are some complex constants, which are of course defined by the function of z by the same formula. But this is there for us. And the series is absolutely convergent. Once we have, or we can express the real part of the function f of z in terms of the complex conjugate of the function f of z. And we write this in terms of series star and its conjugate. We write the right hand side of this expression as a sum of two series. And as for the series for conjugate function, this conjugate function, this series is also absolutely convergent, simply due to the fact that the condition of an absolute convergence includes only the modulus of the series terms. And if this series is absolutely convergent, then the series for f star is also absolutely convergent in the same domain. Then one can, as we have the sum of two absolutely convergent series, one can rearrange the terms in the series, and we can write this. In fact, we can rewrite this series in the form as it is given in the theorem, where one substitute the explicit expression for Cn and the explicit expression for x, for z and z0 in terms of x and y, and then collecting all the terms together at the same powers of x minus x0 and y minus y0, one will have the series of such a function. Nice. Here on the whiteboard, and these two series the terms. For example, let's consider the contribution of this term into this expression. Substitute these expressions. is clear that this expression is real because it is a sum of some complex functions and its conjugate. Then, by simple algebra, one can find that this can be presented in such a form. You see that indeed these two terms can be represented in the form one, the stated from the theorem, and then we just sum this expression with respect to n and collect the terms at equal powers of exponents minus x0 and y minus y0. And the proof is finished.
Election is over.
Okay. Let me stop at this point.